Now we want to look at another aspect of capability, long-term versus short-term data. Data that is taken over a long time period normally have a greater variation, as this data will cover special causes, such as trends in data over time. So here we have the long-term data. As time goes by, you could have, for example, shift changes. You could have weather changes. You could have machine changes or machine degradation over time. If you take data over a short period of time, a lot of those special causes will not be there. There'll be only one shift or one operator or one machine that you're using, for example. And so we can see this here. The variation over the long-term data is represented here compared to the variation of the short-term data is represented here. In our lecture on CP and CPK, we discussed the CP and CPK as indices for comparing the variability of the process against the spec limits. So now thus far we've been given the standard deviation of the process. If we don't know the standard deviation, then we could estimate it using the sample standard deviation as we take samples from our population. But if we take these samples in a short time period, or we take one sample over a short time period, then CP and CPK are really measures of the short-term capability of a stable process. They're going to take into account the variation within each of our samples. So we take a sample, we take a snapshot of the process, we use that sample to estimate the standard deviation, and you can average those values together as we've shown here. So here's the sample. You estimate the standard deviation, sample 2, and you take all of these individual sample standard deviations or sample variances, and you take the average of them to get an overall average standard deviation, which is looking then at each of your samples taken at each time is a short period of time. Each time you have just a short snapshot of your process. You're not taking into account any drift of your process. You're not taking into account any change in the machines or change in the environment. So what you're looking at really is this idea of process potential or potential capability of a process. The CP-CPK represent the potential your process has of producing parts within spec, presuming there's no variation between the samples over time. So to do this, to get an estimation of the longer term capability, we have two new indices, and these are called the process performance capability indices, PP and PPK. And so these are the same. PP is equal to the USL minus the LSL over 6 sigma, and the PPK is equal to the minimum of the USL minus mu over 3 sigma, or the mu minus the LSL over 3 sigma. But the sigma values that we're using here, instead of being based on one sample or the average of many samples, this sigma value should take into account the variation of all the samples over a specific period of time. So you can look at it this way. Here's your different samples, sample 1, sample 2, or sample 1 you calculate the standard deviation, then the sample standard deviation, and overall you can calculate the overall sample standard deviation of over this period of this long period of time. So here we call it S total. And this is actually an X bar here. Hard to see that. We're not asking you to do these calculations. You've done that already. What we're asking you is to understand the difference between the PP and PPK process performance measures and the CP-CPK process capability measurements. The PP and PPK measurements use the overall standard deviation over a period of time. And therefore take into account different types of trends that your data is going to see over time. And so it takes into account things like the shift and the drift between the subgroups. And let's look at some examples to understand this better. Here we have 4 examples. So here we see up here in this corner that the CP is good, CPK is good. I hope you followed that. CP is good because we have very little variation with respect to the spec limits. And the CPK is good because all of these are basically centered with respect to the spec limits. But we also don't see any trend over time, so your PP and your PPK are also good. In this one, we're seeing that the CP is inadequate. CPK is inadequate. CP, the variation is larger than the spec limits. And even though we're centered, the CPK is also going to be inadequate because we're also interested with the CPK at looking at the spec limits. Here, again, there's no change here. Every sample has about the same variation, but because CP and CPK are inadequate, PP and PPK are also going to be bad. Here we have an example where again, CP is good. We've got very little variation, but we're off center. So CP is, well, adequate, it says there. Not great, not great. And because there's no change, though, in this overall, you're going to see the same values for PP and PPK. But now we come to the different one. In this case, at one period of time, we took a couple samples, could look at each one of these CPs, maybe take an average over that time, and CP looks very good. CPK is also adequate. We're not out of spec. We're off center, but we're not out of spec. And you see that also here for both of these cases. During these periods of time, CP is very good for all of these subgroups. CPK is adequate. But overall, if we were to combine this variation, I can't draw that very well here. If we were to combine the variation of all this data, this would bring our PP and our PPK down. The denominator in our equations would go up. The PP and PPK would be low. We look at some more examples. Here you can see, again, this one. Wow, CP for any of these, CP is very good. And we're kind of moving on and off center. CPK is also good. But over all of these samples, you end up with a larger variation because of these trends, whatever's happening there. So PP and PPK are only satisfactory. Here in this example, CPK is also pretty good. CP is pretty good. PPK is adequate. You're kind of not quite out of spec yet. But again, here you're looking at a much larger variation for all of these. So PP and PPK are poor. All right, here, this is okay. Another example down here in this corner, CP is good, CPK is definitely inadequate because you're going out of spec. And again, larger variation means PP is going to be poor and PPK is going to be going out of spec. And here's the last interesting example. You see a trend over time. CP looks good. CPK for every one of these. I mean, some are actually centered, but some are off center. So CPK is going to be satisfactory if we average each of this sigmas together. But in this case, because of this, look at this trend. We're going to have a much larger standard deviation if you take the average of all of those samples together, so your PP and your PPK will be poor. So PP and PPK, there's not more difficult to calculate. You do need to understand the idea that CP and CPK are looking at short-term variation. Typically, then in short term, you have something stable. And so you can, once you get your estimate for sigma, that actually is your potential. That's how good you could do if you didn't have drifting over time. PP and PPK are more stringent. They give you an idea of how your process behaves over the long term. And of course, your ideal situation is to, if we go back one slide, is to be here. Your target in the end would be to have long-term variation, very small and very centered.